Homage! Homage! Come!
All right, ladies and gentlemen, welcome back to 777 Television, your home for everything Matrix Encryption. And I'm your host, Watson Williams, sole owner of the Matrix Encryption patent. In our most recent video, They Picked It Off and Still Lost, we encrypted a plaintext summary of The Hobbit by J.R.R. Tolkien. We created an account and a key set, which we then used to handle the data. The aim of the video was to get viewers to see that when you encrypt proactively, not just blindly trusting platforms, if your data is compromised, it's as useless as an intercepted football that's chained and locked in place. The other team may have possession of the ball, but they can't make any forward progress without the keys. Yes, Matrix Encryption is a symmetric triple key system. After the demo portion, we were introduced to the user origin layer as active rather than passive. The traditional infrastructure stack includes the application layer, the service layer, the infrastructure layer, the networking layer, and the foundational layer. While the application layer acts as an interface with custodial cryptographic services cooked in, we can just encrypt ourselves as a supplementary first line of privacy and defense, not as a replacement to established infrastructure, but as a way to take control of our own data at the source. Earlier this year, I rewrote the payment system on my web server, making the payment system more secure and database-oriented. We implemented a URL secure messaging service previously featured on the channel. And I recently completed a full codebase rewrite for improved state and variable management. Originally, I had relied on global variables, convenient for beginners, but which are notoriously difficult to scale and debug. Now, with Python class objects, the system is fully stabilized, recursive, and auditable. During the rewrite, I solved a previously overlooked edge case for file encryption. And I also uncovered a neat little theorem relating to matrix encryption's resilience, the subject of today's discussion. Now, we need to pay a little homage to Leonard Euler, widely regarded as one of the greatest mathematicians of all time. Euler's number E, the natural exponential number, first related to continuous compound interest in late 1600s finance, emerges from the Horadric Theorem that we're going to be looking at today. Recall that E is the real number that, when taken as an exponential base, is its own rate of change. The derivative curve and the original curve are identical and perfectly overlap. This is interesting as a mathematical parallel between being and becoming, wrestled with as far back as the pre-Socratic Greeks, like Heraclitus and Parmenides, who taught conversely that existence was either governed by constant, unchanging principles, or was in a constant state of flux or change. But then f of x equals e to the x comes along and seems to challenge that fundamental dialectic, saying greetings, my being, and the change in my being are one. Finally, the tangent line, or the instantaneous rate of change of e to the t, is 1, just like the linear function y equals x when t equals 0 at the initial conditions of a system being described. So here's an interesting question. What do Euler's number, cryptography, and the PC game Diablo 2 by Blizzard Entertainment all have in common? Well, they all seem to overlap within a certain area of interest, namely an interest that we will refer to properly as the aggregate search space. The identity of the aggregate search space A sub n and the so-called Horadric Theorem surrounding it will become crystal clear momentarily. Essentially, what we're talking about is the number of possibilities, or the search space, of a particular attack scenario applied to my algorithm. Since matrix encryption is a novel triple key system, various attack scenarios naturally emerge. And the scenario of interest for us is the one in which everything is given to the attacker except the key of order, otherwise known as the shuffle key. The attacker is given the exact master key and the exact codex. They have the encrypted data on a platter and the decryption program needed to recover the original data. Furthermore, we will grant them knowledge of the data type because plain text and file encryptions are otherwise indistinguishable, and the Horadric theorem is not relevant for file encryption. So how hard can it be with just one missing ingredient? Well, the problem is compounded because there's actually a hidden ingredient that needs to be considered. What the attacker will be able to immediately produce in this scenario will be the exact keyboard characters shuffled and completely out of order. Having the correct master key causes any holographic digits therein to evaporate from the encryption, emitting quantum scale heat entropy into the environment according to Landauer's principle. Because of this, no non-determinism in the length of data exists. However, the characters themselves are suspect and subject to questioning. The reason for this is that not all the characters in the unordered message are relevant to the message content, though they all travel together. Sandwiching is a plain text only option, not applicable to file encryption because it would cause file corruption. Sandwiching allows the user who made the encryption to automatically pad the front and back of the plain text with junk characters early in the encryption pipeline. A controlled random number of random characters from the user-submitted codex are applied. And so when sandwiching and shuffling are both engaged, what the attacker has isn't just the right characters out of order, but the right characters and the wrong characters, and everything is commingled and indistinguishable. And so the picture that begins to emerge is a combinatorial inequality, intimidating at first, but which then promptly justifies itself. What we need to consider first is the number of ways to choose m relevant characters out of a total set of n characters. Then we have to count the number of ways to arrange each selection, which is just m factorial. Thus, we arrive at the combination of n objects pick m objects times m factorial, which, through a simple cancellation, is shown to be equal to the permutation of n pick m. Then we can write n factorial over r factorial, where r stands for n minus m. This permutation is necessarily less than or equal to the full permutation space of n pick n, which itself reduces to n factorial. The expression achieves equality if and only if r equals 0, which in terms of our algorithm would mean that no irrelevant characters were added. For a given length, the presence of irrelevant characters can't increase the search beyond the total permutation space. But their addition to a base message contributes significantly to the addition of many orders of magnitude more possibilities and alternative message constructions. Given that the total search space isn't exceeded by the permutation of any sized subset, the Horadric Theorem proposes that the sum of proper subset permutations n pick m is greater, and we run the index from m equals 1 up to n minus 1 to ensure that only non-empty and non-trivial subsets are included. And we call the sum A sub n the aggregate search space. To calculate the value of the aggregate search space, we just need to add together the permutations for all the possible sizes of M. The key is to substitute and express M in terms of n, beginning with large M, i.e. n minus 1, n minus 2, etc., until the aggregate is shown to be larger than n factorial. Note that there is no rule that says we have to sum from smallest to largest, as our sigma index indicates. The commutative property of addition ensures this. When we simplify, we see that n always cancels in the denominator, leaving a positive integer from out of the parentheses. Already we can begin to explicitly write a sub n, and notice that the aggregate will be larger than n factorial because the first term is already n factorial. Then additional terms are added up to the kth term. So the Horadric theorem is true, but where does E come from exactly? Around 1730, Euler showed that E can be expressed as the infinite series of 1 over n factorial, with n indexed from 0 to infinity. This expands to 1 over 0 factorial, plus 1 over 1 factorial, plus 1 over 2 factorial, etc., which is relatable to our expansion of permutations without the leading term. In order to substitute, we first factor n factorial out, since it is present in every term up to k. Subtracting 1 from both sides of Euler's infinite series reveals an identity with the limit of our parenthetical term, and thus we can express the limit of the aggregate search space normalized over n factorial so that it converges rather than diverges to e minus 1 as n goes to infinity. Interestingly, by re-indexing to include m equals 0, we can express e itself rather than e minus 1 as the limit as n goes to infinity of 1 over n factorial, again that's the synthetic normalizing term, times the sum of permutations of n pick m with m running from 0 up to n, or n minus 1. Really, the upper bound of the index doesn't matter because the limit is going to infinity anyway. No matter the size of n factorial will always factor out of every term in the sum and will then cancel with the normalizing term in the front, resulting in the exact value of e at infinity. Stay tuned for part 2, where we will tie in the relevance to Diablo 2 and summarize the discovery and exploration of Euler's number E deep within the best case attacker, everything but the shuffle key scenario, and then finally relate the expedition back to the entire matrix encryption cryptographic system. Thank you for watching, and take care.